Everyone and welcome back. I hope the new semester has been treating you well and that you all have settled in comfortably. As a part of our effort to make it more exciting, Singularity is launching its Student Talk series, a platform where students get the spotlight to share their ideas, research and passions with the community. And for the very first talk, we have someone you all know, Eklavya Kukrety from 22 MS from the Department of Physical Sciences. He is not just into mind-bending physics, but also the OB of our tennis club. Today, he will be speaking on dark matter captured in neutron stars. In his talk, Eklavya will walk us through his summer research on dark matter, starting from its historical evidence, moving into the fascinating process of dark matter captured in neutron stars, and finally examining how this capture influences the tidal deformability of neutron stars. So sit back, get curious, and let's welcome Eklvya on stage.
Hello, good evening everyone. Am I audible?
Yes.
Okay, so I am Eklvya Kukrety from 22 MS and today I will be presenting my summer research work on dark matter capture in neutron stars and its significance, which I did under Professor Malik at IISER Bhopal. So, in today's talk I will be talking about history of dark matter, followed by dark matter capture in neutron stars, the theoretical framework, two-fluid TOV approach, then few of the results which I got using that. And for the significance part, I will be talking about tidal deformity and how tidal deformity changes when dark matter is added to a neutron star. So first, what is dark matter? So over the past few decades, the very meaning of the phrase dark matter has evolved. So today it is mostly used as a proper noun to describe whatever the particle species account for the bulk of our universe matter density. Earlier, this phrase was a mere adjective, well, dark was a mere adjective and it included all varieties of astrophysical material that happened to be too faint to be detected with available telescopes. And for evidence for dark matter, so mainly we have three main evidences for dark matter. First is the velocity dispersion of galaxies in cluster, then galaxy rotation curve, and gravitational lensing. So we'll look into each of them. So first one, velocity dispersion of galaxies in cluster. So Swiss-American astronomer Kukrety was arguably one of the most famous and cited pioneer in the field of dark matter. In 1933, he studied the redshift of various galaxy clusters and he noticed a large scatter in apparent velocities of 8 galaxies within chroma cluster with differences that exceeded 2000 kilometers per second. He theoretically calculated the mass of the chroma cluster using Virial theorem and concluded that they should exhibit a velocity dispersion of 80 kilometers per second. So, like theoretically it was coming out to be 80 and from the evidence we have seen that it is 2000, from the observation evidence we have seen that it is 2000 kilometers per second. So, from this we concluded that if this would be confirmed, we would get a surprising if this would be confirmed, we will get the surprising result that dark matter is present in much greater amount than luminous matter. This was not the first use of the phrase dark matter, though many wrongly believe it to be. Then second evidence. Second evidence is galaxy rotational curves. The rotation curves of galaxy is the circular velocity profile of the stars and gas in a galaxy as a function of their distance from galactic center. This played a crucial role in discovery of dark matter. So according to Newtonian gravity, we know that outer stars should move slower if the mass was concentrated in the galactic center. We can see this using a simplified formula like This is for uh, bodies which are at a greater distance from the galactic center, as we are considering the mass of the galaxy to be concentrated at the center. So for the galaxies which are very close to the center, the mass distribution is different, so this is not followed. But for the galaxies, for the stars which are far from the galactic centers, we can see that their velocity should decrease as 1 by square root r. And however, in 1970s, astronomers like Vera Rubin and W. Kent Ford Jr. Found that the rotational curves of many galaxies were flat, meaning that stars at the outer edges of galaxies were moving at speeds similar to those closer to the center. So we can see it in this graph that this bottom curve is the expected velocity profile, and this one is the observational velocity profile. So this was unexpected, as it suggested that there was more mass in the outer regions of the galaxies than could be accounted for by visible matter alone. Then the third evidence is gravitational lensing. So gravitational lensing is a phenomena where light from distant object is bent by gravitational field of a massive object like a galaxy or cluster of galaxies, which is lying between the observer and the distant object. So the amount of lensing observed in the clusters like bullet clusters often exceed what visible matter can account for. So using this, we can conclude that there is some dark matter, as the lensing effect is proportional to the total mass of lensing, including both visible and dark matter. So like this is Earth, so we are over here, and this is the galaxy which is being, the light is being bent around the some massive astrophysical objects like galaxy or cluster of galaxies. So what is dark matter made up of? So the proposed candidates for dark matter were standard model neutrinos. These were later rejected. Supersymmetric particles, axions, and WIMPs, weakly interacting massive particles. So neutrinos are stable and they do not experience electromagnetic force or strong interaction. These are essential characteristics for any viable dark matter candidate. It was later found out that standard model neutrinos were far too light and relativistic to make up dark matter. So although today we know that dark matter is not made up of neutrinos, they provided an important template for the hypothetical species that would be later known as WIMPs, weakly interacting massive particles. Supersymmetric particles. Supersymmetry is a theoretical framework that extends the standard model of particle physics by proposing symmetry between fermions and bosons. So supersymmetry predicts existence of several electrically neutral and non-strongly interacting particles like superpartners to neutrinos, photons, etc. So the minimal supersymmetric standard model predicts existence of a lightest neutralino. Over the past 3.5 decades, neutralinos, a stable electrically neutral particle which does not interact via strong force, has been one of the most studied candidates for dark matter, and it has been discussed in thousands of scientific publications. But other candidates like S neutrinos, which are supersymmetric particle to neutrinos, were also predicted, but there has not been any experimental evidence for any of these particles. Axions. Axions are hypothetical elementary particles that were proposed in 1977 to solve the strong charge parity problem in quantum chromodynamics, which is the study of strong interaction between quarks mediated by gluons. They are predicted to be very light, electrically neutral, and weakly interacting, making them a potential candidate. But similarly, there has been no experimental evidence. Weakly interacting massive particles. So scientists studying dark matter noticed that many of the proposed dark matter particles shared similar traits like dark matter particles can't be too light. It should weigh roughly around 1 to 100 kilo electron volts. And additionally, for these particles to match the amount of dark matter we observe today, they must self-annihilate at a cross section of about 10 to the power minus 26 centimeters per second. So this rate is very close to the cross section of weak nuclear force interactions. So this observation, combined with the theoretical arguments in favor of existence of new physics around the electroweak scale, has elevated WIMPs to be the leading class of candidates for dark matter.
The way is it that to be like the way how is it in electron volts?
Oh, we can, like, from mass energy equivalence we can convert like grams or kgs to.
And what is the significance?
The amount of dark matter which we observe today, so for that it should have a self-annihilation cross-section rate which is close to this, and this exact same rate is very close to the cross-section rate of the weak nuclear force interaction. So like based on the same rate, scientists propose that like weakly interacting particles can be a candidate for dark matter.
Okay, I'm in second year, so I don't understand any of the terms.
So actually, I have also not studied particle physics, so.
Oh.
So someone can ask why not baryonic dark matter. So as the evidence in favor of dark matter in galaxies and galaxy cluster accumulated, more and more astronomers began to contemplate what might make up this faint material. So the most obvious candidate was less luminous baryonic matter, which is the ordinary matter that makes up stars, planets and other celestial objects. So Kim Grice coined the term MACHOS, or massive astrophysical compact halo objects, to denote this class of dark matter candidates in response to the leading alternatives to WIMPs. So, but now it is a general consensus that massive baryonic matters can't account for bulk of the dark matter in our universe. The two main reasons for this are gravitational microlensing and cosmic microwave background observation. So, gravitational microlensing is the same as microlensing, same as gravitational lensing, but in gravitational lensing the light is bent by more massive objects like galaxies or cluster of galaxies, while in microlensing the light is being bent around relatively smaller objects like stars. So, like over a period of 5.7 years, the MACHO collaboration measured the light curves of 40 million individual stars and identifying between 14 and 17 candidate microlensing events. This led them to conclude between 8 to 50% of our Milky Way's halo's mass consists of compact objects. Okay. Light can be reflected around by gravity. Right.
Measure the light curve. You were asking the meaning of light curve.
Oh, light curves, I mean, I didn't get exactly what that.
Yeah, that's the
In the second term, you have to look at it. Collaboration measure the light curve. What is light? What is asking?
Means there were observation of 40 million different stars, basically. The path of light. Path of light. Like when there is a body between the source and the observer, then light can bend around it, which is known as gravitational lensing.
How do we measure that density?
For which is that we can use general relativity to measure the amount of.
That's theoretical. The
Yes.
general is theoretical, but how do we actually?
So we can observe, in lensing, many times we observe multiple images for the same object which is we are observing. So using that we can similarly, EROS collaboration collected data for 6.7 years, but it had identified only one microlensing candidate event, allowing it to place an upper limit of 8% on the halo mass fraction, 8% limit of dark matter. So this led to conclusion that compact objects, at least within the mass range probed by microlensing surveys, do not appear to dominate the missing mass in Milky Way's halo. Then cosmic microwave background observations. So cosmic microwave background is the afterglow of Big Bang. It is a nearly uniform background radiation that fills the universe and provides a snapshot of early universe. Scientists found out that deuterium, which is heavy hydrogen found in space, could not come from stars and it had to be made during Big Bang. Scientists used its abundance to estimate how much of the normal matter, baryons, exist in our universe, finding it only 10% of the critical density which is needed to explain cosmic structure. Later, precise measurements of deuterium and cosmic microwave background by experiments like WMAP and Planck confirmed that normal matter makes up less than 20% of all the matter in the universe. It is one of the experiments which was used to.
What's exactly this in context?
WMAP is a experiment which was used to measure the level, amount of deuterium in our universe. Observation. I don't know the full form of it. So this means that vast majority of matter in the universe is not baryonic, but rather some other form of matter, which we refer to as dark matter. So now I will be moving to the dark matter capture in neutron stars part. So I will give a brief introduction on neutron star. So neutron star is the gravitational collapse core of a massive supergiant star that has undergone a supernova explosion. They are supported against further gravitational collapse by neutron degeneracy pressure, which is a quantum mechanical effect arising from Pauli exclusion principle along with strong nuclear forces. And neutron stars are incredibly dense with a mass typically between 1 to 2 solar masses and with a radius of about 10 to 20 kilometers. So why do we use neutron stars to study dark matter? So neutron stars are incredibly dense and compact, so it provides a unique environment where dark matter can interact with ordinary matter. Strong gravitational field of neutron stars can capture dark matter particles, allowing for their potential detection and study of their properties. The interaction between dark matter and neutron stars can lead to observable effects such as changes in mass radius sequence or stars cooling rate. So I used a two-fluid POV approach. So the Tolman-Oppenheimer-Volkoff equations are a set of coupled differential equations which describes the structure of a spherically symmetric body in hydrostatic equilibrium under the influence of gravity. We get this upon solving the Einstein field equations of general relativity, and we'll be looking at the two fluid formalism. We will also need to model equation of state for a star. Like the outward forces, pressure forces due to neutron degeneracy pressure and storm forces is counters the inward forces due to gravity. This is in hydrostatic equilibrium. Yes, it is modeled as a fluid. Stars are modeled as a fluid. That's why hydrostatic. We will also need to model equation of states, as without complete description of equation of states, we cannot solve TOV equations. So, equation of state is a thermodynamic equation that relates macroscopic state variables such as pressure, temperature, and volume of a system. In context of neutron stars, equation of state describes how pressure and energy density are related. It is crucial for understanding the structure and stability of stars. We will need to model two different equations of states, one for the neutron star matter and another for dark matter. So, the blue one is the equation of state for dark matter, and the yellow one is the equation of state for nuclear matter. So on x-axis it is the energy density and y-axis is pressure. Two fluid TOV. So to study the property of dark matter amidst neutron stars, we adopt two fluid formalism where nuclear matter and dark matter do not interact directly, but rather the interaction between these two sectors is only through gravitational interaction. So the dark matter amidst neutron star structure can be obtained by solving hydrostatic balance equation, the TOV equation. And the TOV equations are given as this, where P1 and epsilon 1 are the pressure and energy density for star 1, and P2 and epsilon 2 are the pressure and energy density for the second, like one is for the neutron star like baryonic matter and one is for the dark matter. So here we are using G is equals to C is equals to 1, so natural physics. And on while solving two fluid TOV, we have to give along with equation of state, we have to provide two more parameters: the central energy density for neutron star matter and central energy density for dark matter. These are the inputs while solving TOV. And we can solve this using by directly integrating it. So I did it using RK for integration. So these are the results. So first I performed two checks to see the compatibility of the two fluid TOV code with the single fluid TOV code. So for that I checked, I compared the pressure profile and mass distribution and MR, mass radius sequence. So the fraction is defined as the mass fraction of dark matter. So mass of dark matter divided by total mass of dark matter plus mass of nuclear matter. So the above one are the graphs for the single fluid using single fluid TOV code, and this is the graph using two fluid TOV code. So first, this one is the pressure profile using single fluid TOV code, and this is for the pressure profile using two fluid TOV code. In this case, I have considered the fraction to be 0 to check the compatibility of the graphs, and this is similar for the mass distribution within a star. This is first column is for pressure distribution within a star, and second column is for mass distribution within a star. Then next I compared the MR sequences. So like in the MR sequence, like each point is a different star. Like this does not relates. This does not relate the mass radius of a single star. Rather, each point on the curve is a different star, and this is the total mass of the star, and this is the total radius of the star. So, for plotting this, I used the central energy density range between 120 and 1600 MeV per Q. And in this graph also I have considered dark matter fraction to be 0. So by both of these graphs we can see that confirm that our two fluid code was compatible with the single fluid POV code. And next, this is the mass radius sequence for two fluid TOV code, like using various dark matter fractions. So the purple one is for 0 dark matter fraction, blue one is for 5%, green is for 10%, and yellow is for 15%. So like similar to the single fluid case, like each point on this curve is a star, and we can see that as we increase our dark matter fraction, the maximum possible mass for the neutron stars is decreasing. Like this is the maximum possible mass, like just above 2 for 15% dark matter fraction, and like for 0 dark matter fraction it's around 2.5. And so like in neutron stars, the star having more mass is actually more compact and have lesser radius, while star having less mass is less compact and has more radius. So the stars which are to the left of the highest mass of for each curve are actually unstable. So like upon increasing our central energy, we can see this using different graph also, which I have plotted later using mass versus central density, but we can also observe it using this, that for stars which are having central density more than the central density of the highest mass star are actually unstable, because as we increase our central energy density, the mass of the star should increase. So, but after this point, the mass of the star is actually decreasing, which is physically not possible. So, like these are actually not stable stars, which are to the left of the maxima. Then these are the pressure profile and mass profiles for various dark matter fraction. So, like you can see the radius for dark matter inside the neutron star is actually increasing as we increase the dark matter fraction. So like around dark matter fraction 0.057, the radius of the dark matter inside the neutron star is approximately equal to the radius of the neutron stars, and upon increasing it to like 0.25, the dark matter is actually forming a halo structure around the neutron star. So I have tabulated the results over here.
How does it form a halo
structure? This is for the equilibrium state. Like this is not a dynamical model system which I am modeling. So here, like I have considered for like dark matter fraction about 0.25. Actually, the radius of the dark matter is exceeding the radius of the neutron star. So, like it is going from r is equals to 0 to about 19 kilometers, while the neutron star's radius is actually only around 11.2 kilometers. So, like it's present around the neutron star also, and it forms like a halo kind of structure. And this is the mass versus central energy density curve. So over here, these are the points for the maximum stable star which we can observe. So the stars to the right of this are actually unstable because of the same reason which I told before, that upon increasing central density, our mass should not decrease. It is physically impossible for the masses to decrease on increasing central energy density. Then I'll be giving a brief introduction to tidal deformity. So, neutron stars are incredibly dense and compact objects, and understanding their internal structure and ultra-dense nuclear matter they are composed of is a major challenge, and direct observational constraints on neutron stars are limited, making indirect methods crucial. So, one such powerful method involves studying tidal deformity. When a neutron star is subjected to an external gravitational field, such as in a binary system or with another compact object, it deforms. This deformation induces a quadruple movement in the stars, and the extent of the deformation is quantified by tidal deformity. So, tidal deformity is directly related to the star's internal structure and crucially to the equation of state of the matter within it. By measuring tidal effects in gravitational wave signals from spiraling binary neutron stars, we can gain valuable insights into fundamental properties of nuclear matter at extreme densities, which are otherwise inaccessible.
What do you mean by increasing of quadruple movement in the star?
Like while derivation, we can see that actually
How do you
physically I am not so sure because like I have cited the paper. So in this actually I have not covered the whole calculation because it was very lengthy, so but you can check the cited paper for more details. I have provided the link for this in the references actually because actually it's very long calculation. So I'll just be giving a brief overview for the derivation. If anyone is more interested, can refer to the cited paper. So we start by describing the space-time geometry of a static spherically symmetric stars using QOB equations. So, and the geometry of spacetime for a spherically static stars can be described by the line element this. Stress energy tensor is given by this. We can then numerically integrate the TOV equations to get the equilibrium state for a neutron star. Then due to tidal effects, actually there are perturbations in our metric. So G alpha beta naught is the unperturbed metric and this is the perturbation term. Then we analyze the angular dependence of the components of perturbation in spherical harmonics. This was done by Reg and Wheeler, and using if we restrict our analysis to L is equals to 2 static even parity perturbations in Rege-Wheeler gauge, we can write the perturbation in this form, in spherical harmonics. So, if anyone is interested, can go through the paper for this derivation. And by substituting the perturbed metric and stress energy tensor in Einstein equation, we get a second order differential equation for H, where H of R is defined as minus H2, which is equal to the H naught, the terms which were over here. So we get this second order differential equations. Then we match the boundary conditions like the solution for H must be regular at center and outside star. In the vacuum region outside star, the differential equation simplifies. Its general solution can be expressed in terms of Legendre functions containing two integration constants C1, C2, and these constants are directly related to the induced quadruple moment Qij. and the external tidal field Eij through this relation, where the lambda is related to K2. K2 is the tidal love number. The interior and exterior, like we can just match all the solutions and we define a quantity y which is related to h and radius, and we solve the differential equation of phi to, so we get the final expression of K2 over here, where c is the compactness, which is defined as mass of the star upon radius of star, and we can solve for y using they are provided over here, this differential equation. So tidal deformity characterizes how neutron star deforms under an external tidal field. This is for the single fluid formalism. So for a single fluid neutron star, it is given by 2/3 of tidal love number times 5th power of inverse of compact. And tidal love number K2 is the same one which I have shown in the previous slide. It is typically around 0.05 to 0.15 per neutron star. And we get y on solving the following differential equations. For f and q are defined over here. So this was the plot for tidal love number versus mass for a single fluid star. So we can observe
Can see from the graph that the K2 decreases monotonically with mass. So this implies that the low mass neutron stars are less compact, hence they have a bigger radius, and therefore they have higher K2 values, whereas the high mass neutron stars are more compact with a smaller radius and they have lower K2 values. These conclusions are given on the next slide. Then this is the graph for single fluid neutron star tidal deformity. So we know that we have seen that the tidal deformity is given by the given formula, like it is proportional to the radius by mass to the power 5. So as the tidal deformity decreases sharply with mass, therefore the curve is steep and is plotted on logarithmic scales, and as mass increases, K2 decreases, but the compactness decreases more rapidly than the the decrease in K2. Hence, this leads to an exponential drop in tidal deformity. Then, coming on to the two-fluid formalism, we can see that the expression for tidal deformity is same, and the differential equation is also the same, but the function f and function q are modified to accommodate the two fluid formalism. So we can see it in this slide. Then few important points to note are both formalisms require solving the TOB equations with appropriate boundary conditions, and for two fluid formalism the equation of state must be specified for both neutron star matter and the dark matter separately, and the matching at the surface uses the same form but with modified interior solution. This means that the functions which I just told earlier, the functions f and q are modified for the two fluid formalism. Then this is the graph for the two fluid neutron star tidal deformability. So we can see that this is the graph for two fluid tidal love number. So as we can see from the graph that as dark matter fraction increases, the curve shifts downwards. This means that the stars which have more dark matter are less responsive to tidal forces, and hence they are more compact and rigid. But an important point to note is that this is sensitive to our choice of equation of state, and it may vary with different equation of states. So next, moving on to the tidal deformity for two fluid case. So here also we can see that as the dark matter fraction increases, the tidal deformity decreases for the same mass. This aligns with the decrease in the tidal Love number K2 and potentially smaller radius due to gravitational compression by dark matter. This is the graph again. Okay, thank you, and here are the references if anyone is interested to go through them. Thank you.